result from AMS. So please welcome Professor Chang from National University. National Central University.
Thank you for the invitation to give this report on AMS result. I want to report the latest development of AMS. But before doing that, I have an advertisement. There will be a special colloquium by AMS spokesman Samuel Ting. There's one line missing here. It's a time. Sorry. Somehow it doesn't show up. It's a Thursday, 5 p.m. at CERN, which is Thursday midnight in Taiwan. In that talk, the talk title is The First 5 Years of the Alpha Magnetic Spectrometer on the International Space Station. In this talk, there will be many new results announced or published there. So it's fortunate or unfortunate for me that many of these new results I cannot speak of today, report on published results. So let me come to first to make a very short introduction to the AMS experiment. This is AMS. It's a space-borne magnetic spectrometer. So the central part of the AMS is a magnet. It's a permanent magnet with 1.5 kilobars of magnetic field. In the magnet, we have installed from top to bottom 1 to 9 layers of silicon detector made of silicon microstrip detectors, giving about 10 micron resolution for tracking. And this makes the spectrometer, and on top of the spectrometer, there's a transition radiation detector which separates electron positrons from protons, and then followed by time-of-flight detector, which measures the velocity and also functions as a trigger to the electronic system. And in the bottom is a ring image Cherenkov detector, which measures velocity with about 1 per mil resolution, and an electromagnetic calorimeter, which measures the energy of EM energy and also separates electron positron from the proton. So this detector was launched to the International Space Station by Shuttle Endeavour on May 16, 2011. Here you see the shuttle punch through the overcast cloud. And so since then, the detector has been operational on the space station without any major hardware failures. So it's actually just roughly continuously taking data for 5 years. And we have collected more than 85 billion charged cosmic rays during this period. The AMS team has organized this in such a way that for every physics subject, we have at least 2 independent analysis, or sometimes more for every subject. And the results are published only when all these analyses are in agreement. So let me now come to report the results. I put the result in 2 categories. One is a search for the dark matter, which involves positron fraction, electron and positron spectrum, and the anti-proton to proton ratio. I think this is now well known that one of the most favored dark matter candidates is the WIMP, weakly interacting massive particles, such as supersymmetric neutrino. They are assumed to annihilate with themselves and produce quarks and leptons. Eventually, they become electron, positron, antiproton, and protons that are detected by the space detectors. Now, because of positron and antiproton has much smaller flux in the cosmic rays, so these 2 are the most sensitive probe that we can test the existence of dark matter. And this idea has been proposed very early on, 1990, by, for example, Chang1 and Yuan. They proposed to measure the positron to electron plus positron plus electron, so-called positron ratio. From normal cosmic ray collision, we produce positrons. So there is a nature or background spectrum which tends to decrease as energy increases. However, with the injection of positrons from dark matter annihilation, we expect some increase of the spectrum, the ratio. Up to some point, it stopped to increase and dropped off because of the cutoff, right, dark matter and mass. And actually, that was this was a measurement. It's very insistent. Now I lost the complete. No, I didn't get. Sorry. Okay. So this was the very first publication. The result was the first publication from AMS in 2013. We have, at that time, 6.8 million electron and positron events. And indeed, we see an increase of the spectrum. In 2014, we updated the result with 10 million electron and positron, and we tried to see several features of the possible dark matter signal. The features including first the low energy, it has to agree with the cosmic ray collision model, and then we observed the increase of the spectrum, the ratio. At some point, the ratio stops increase and start a very rapid drop at high energy because of the mass limit. Now, another feature is the isotropic, whether it's isotropic or anisotropic. For dark matter, we expect an isotropic distribution of the positrons. Now, at low energy, indeed, we see that the spectrum agrees with the prediction from cosmic ray collisions. However, at 6 GeV, you see a deviation and very rapid increase of the ratio of positron. And this ratio, if I plotted in linear scale up to 500 GeV, is in agreement with previous measurement by Pamela and Fermi. They have reported this phenomena prior to AMS. However, AMS extended the measurement to 400 GeV, and indeed we see that the spectrum stopped to increase and come to a plateau at around 300 GeV or 200 to 300 GeV, and even start to decrease at higher energy. And we measure the slope of this curve, and it looks like the slope is linearly decreased up to 270 GeV and cross zero. So we determined that at 270 GeV it comes to a peak and looks like it starts to decrease. But this, unfortunately, cannot tell for sure whether this is a positron, is a dark matter or some astrophysical sources like pulsars. For example, a nearby pulsar will produce similar spectrum, except at high energy, it should decrease smoothly rather than a rapid decrease because of dark matter production. So this is these points are just simulated events points for future for the operation up to 2024, which is currently our goal of operation. This year, we have again doubled our statistics, and with about 20 billion electron and positron events, which is twice as much as the previous publication. The result is just increase 1 point, and so you can see the difficulty of this experiment, that the statistics at this high energy region is very, very small, and it takes a very long time to accumulate data. Unfortunately, this point doesn't tell much. It's still with very high statistical error, and also it seems to follow. You can explain it in any different ways. So I think conclusion is that from this measurement alone, we have to wait more statistics to give us a really conclusive answer. Now, I've mentioned that isotropic, whether it's isotropic or anisotropic, is an issue to separate the pulsar model, a nearby pulsar, or whether this extra positron is from dark matter. Now, this red line is what we expect from an isotropic measurement of this parameter delta, which is the dipole component of the distribution. The yellow band shows the 1 sigma of this measurement. Now, our measurement right now is here, which is well within the 1 sigma of what we expected from an isotropic distribution. However, again, this is not enough to separate the model of pulsar or a complete isotropic distribution expected from dark matter. We expect that with this increase of statistics, eventually we will be able to make this separation. Now, the second measurement we reported is the electron and positron spectrum separately, not a ratio, but separate the electron and positron spectrum. And here we show the spectrum of positron and the electron. You see that they have very different features. Note that the scale is different by a factor of 10. We see that the positron has a clear increase of flux at about 50 GeV above. Now, we also notice that if you extrapolate this line, the electron also has an increase of flux. So this gives us an indication that the excess of positron ratio is coming from extra injection of particles rather than some deficit of electron. So this picture also confirms that our understanding that probably this is some unknown new source. Now, in this year, with more statistics, we have one extra point, and this is the positron spectrum now. This picture is very, very suggestive. You can almost see a peak structure or a bump. But I want to emphasize that the error bar is still very big. The statistical error dominated the error here and also here. So it's still too early to say that this is really a structure. We still have to wait for more statistics to be sure. But certainly this is a very interesting feature that we've seen with this year's statistics. Electron and positron, we have already seen that there is something peculiar. But this because of its light mass, electron and positron can be produced in many different processes, including like pulsar or inside supernova explosion. However, we have a complement measurement that is the antiproton to proton ratio. Antiproton is heavy, so it's very difficult to produce inside pulsar. And our measurement shows that the antiproton to proton distribution is roughly flat, actually quite flat, up to a few hundred GeV. This is rather unexpected. These two are just two models, cosmic ray models, one without dark matter, and in general we expect a decrease of the ratio because antiproton is a secondary particle. The ratio we expect to somehow will decrease with the energy. And this very broad bump comes from the annihilation of neutrino of about 1 TeV. So indeed, we may interpret this flatness of the spectrum as a result of this broad enhancement of antiproton. However, as you can see, these models have very big error, and this is also just one of the many models. So, although antiproton is more difficult to create in the galactic, interstellar material, the uncertainty is also very big because it's a very broad distribution, and it's not like you can tell there's a very strong structure. So this is up to now the status of our measurements concerning the dark matter search. One quite unexpected observation we have made during this measurement is that if we plot proton, electron, antiproton, electron, and positron in the same picture, of course with different scales, you see that very surprisingly, antiproton, positron, and proton all follow the same power law, while electron has a very different behavior. This is, again, hard to understand because proton is a primary particle, cosmic ray. Electron, positron, and antiproton are all secondary in nature. Furthermore, antiproton and positron has very different propagation properties because of difference in mass. But for some reason, they all come to the same spectrum at the end. I think this is really a challenge to the theory to understand why it is. Is this an accidental result, or there's some physics mechanism behind it? We have yet to understand. The second subject I want to discuss is unveiling the origin and propagation of cosmic rays. In this section, we have measurements of electron plus positron spectrum, proton, helium, boron, carbon, lithium spectrums, and their ratios. I want to remind you that this positron, the dark matter assumption are based on a difference from the cosmic ray model without dark matter. This cosmic ray model has very big uncertainties. Now I give you a more extreme example. This is from this paper, Kosick and colleagues. Our traditional cosmic ray model gives positron refraction that decrease with energy. But their model, so-called nested leaky box model, can explain the increase of positron fraction by changing the distribution of intergalactic interstellar material. And they can actually fit the data very well and even predict this decrease of spectrum at higher energy, which we have more points that slightly decrease from the peak. So this is, looks like a very good model. However, with this model, they also predict that boron to carbon ratio follows this blue line here, which is in disagreed with our measurements, which follows a pure power line to higher energy. So you see that there can be a model without any dark matter injection, but this model has its consequence that in other measurements they don't agree. I think a good model has to predict not just the positron to electron ratio, but all the fluxes of proton, helium, boron, carbon, lithium, and everything else. And that's a huge task. It's a very difficult task to do. But however, without such a cosmic ray propagation model, I think it will be very difficult to interpret the data to say for sure that it's a dark matter or from some other sources. Now, unfortunately, this is a very difficult job because the transport, for example, one of the model called the ScalePro program developed by Stanford University, and they try to solve the transport equation of about 90 cosmic ray species. This transport equation is based on hydrodynamic diffusion of cosmic rays in the galactic material, in the stellar material. And there are many parameters, this diffusion, spatial diffusion, diffusion in momentum space, and the source, the boundary conditions. All this has to be constrained by data. So every measurement, whenever we added one more measurement, we add more constraint to this model, and we can have a better prediction of what's the cosmic ray spectrum. Now, AMS has very good charge separation. This picture shows the full statistics of as a charge measured by time of flight and from tracker. So you can see very clearly the peak of every element up to iron. And that means we can produce actually very good spectrum for every element. It takes time, but gradually we want to have measurement of every of these elements up to iron or even nickel here. So I give you just the status up to now. First is our measurement of electron plus positron spectrum. This is AMS measurement. And this is before AMS, most significantly from the Fermi lab measurement. You see a very clear difference, very clear disagreement between them. But most of the cosmic ray model that existing are based on this line. And with AMS result, I think many models has to readjust their parameters. And this curve can be described quite well by a single power law. So there's no feature, just a single power law up above 30 GeV. Now the second measurement is the proton measurement. AMS get this result, this spectrum with 300 million events. It's a huge statistics. And before AMS, the blue and green dots are from Pamela and other experiments. They see the spectrum and they see some kind of break of the spectrum in the spectrum at around 200 GeV or 300 GeV. But this with very high uncertainties, and also the points tends not to each experiment tends not to measure the continuous through this period. And AMS is the first experiment provide precise data through this breaking region, this energy range. And indeed, our measurement shows that there's a very clear break of the spectrum at about 200 or 300 GeV. And the single power law is ruled out at 99.9% confidence level. And this kind of break of spectrum, power spectrum, sorry, by the way, this is the proton spectrum times rigidity to the 2.7. It's not very clear, but it's times rigidity to the 2.7. And this is the rigidity. So this kind of break of power law normally means that there are new physics mechanism gets involved at this point. We don't know yet what it is, but this is now a very firmly established result. Another interesting thing that we have seen is the agreement between the Voyager measurement and the AMS measurement. Voyager measured the cosmic ray flux outside of solar system. They are already out of the heliosphere, and the spectrum looks like this. Of course, they measure only low energy proton. However, this and AMS result can be very well described by a single theory with solar modulation. So we can see very clearly the solar modulation effect of solar modulation that brings the spectrum outside of solar system to inside of near Earth orbit. That's a very amazing agreement. Now the next measurement we published in 2015 is helium spectrum. Again, we see that the AMS measurement, the red points, based on 50 million events, goes across the region where we previously has an indication that there's a break of the power spectrum. Here, Pamela even claimed that there's a deep and then a sharp break and increase of the spectrum line. AMS, again, provide the first smooth measurement with high precision across this region. And our measurement again shows that indeed there's a break of two power lines, power spectrums at about 200 GeV to 300 GeV. Again, single power law fit rule out at 99.9% confidence level. So the surprising result is the proton to helium ratio. Now, traditionally, we believe that since proton and helium are both primary cosmic rays produced from the supernova, their rigidity has to be flat. The ratio of the rigidity has to be flat at higher energy. So this is the prediction of most theories. However, our measurement says different. That the rigidity actually follows continuous decreasing rate to very high energy. So this is something that, again, is not understood and has to be really clarified. Followed by this measurement this year, we have measured carbon and the boron results. You see the carbon results, it's almost flat at high energy. Because this flux has already multiplied by energy to 2.7, so this flux actually goes to has energy to the minus 2.7. It's roughly flat here, and we don't see very clear break of power index, but maybe there's some sign, not very clear. And also the boron nucleon. Boron has a different behavior that clearly it's softer than 2.7, e to the minus 2.7. So this is rather like e to the minus 3 in the power index. So comparing the carbon and boron, you see that the spectrum are very different. And this is mostly because we believe that because boron is a secondary cosmic ray particle, but carbon is believed to be a primary from the supernova. And their ratio, the ratio between boron and carbon gives us a very good indication of how the elements propagate in the intergalactic, interstellar material. Carbon, nitrogen, oxygen are believed to be primary. They are produced and then they propagate through the galaxy, and they interact with interstellar material and produce secondary particles like boron, and eventually they are detected by the AMS. So there are models to